Okay, on to the third subtopic in the light and matter topic, which is photons, and we're going to look in this first video at the photoelectric effect. These concepts are really, really important in terms of how X-rays work. We're going to cover that in this topic. They're important in terms of how solar panels work. They're also important in how the solar sails work that we covered earlier in the year. And they're important in lots and lots of other scientific examples, but they're probably the most important practical examples. Okay, so let's talk about photons. And before we do this, and for those of you who watch this in class with me, I'll get you to watch this TED Ed video to start off with. Those of you who are watching this on the YouTube, please go and look up this TED Ed video and watch this probably right now before I even start talking about this. It's going to give you a really good introduction to the sort of thing I'm talking about. So up until now, we've been looking at light as an electromagnetic wave. So as a transverse wave made of an oscillating electric and magnetic field. And we talked about how that's formed in the electromagnetic radiation topic. And then if you like, in the interference of light topic, we looked at all this evidence that suggests light behaves like a wave. Because when we see an interference pattern between two waves, we see constructive interference when two waves that are in phase meet, or destructive interference where waves that are out of phase meet and cancel each other out. All this is evidence that light is behaving like a wave. However, it does not explain all of the observations we see of light, because sometimes when we look at how light behaves, it behaves rather than like an electromagnetic wave, it behaves like a little particle, and we call that little particle a photon. So, and the energy of that photon is given by E equals hf, where E is energy, h is Planck's constant, f is frequency, and its momentum is given by this equation here. We'll look at those in some problem-solving examples. They're fairly straightforward. We'll also, in the lab, work out an estimated value for Planck's constant, which is given here. If you like, our true value, which is given there. So, what is some of this evidence that suggests light is behaving like a particle rather than a wave? Firstly, if we consider an image being created on a photographic film in a double-slit experiment, if the light was of very low intensity, we might expect to see the image start off very, very faintly, but even and over time become more intense as the light strikes the film. So this image would start off as very faint and it would just get more intense, more intense, more intense. But even when it's really, really faint, the image would be there. It would just be a faint image. However, what happens is the image builds up as a series of discrete dots successively appearing over time. This indicates light is not reaching the film as a continuous wave, but in discrete individual bits, almost equivalent to individual particles or photons of light hitting the film. So we've demonstrated this here, what we might see if we use really low intensity light, as we saw the image build up using a green laser for the double slit experiment. So it starts off as just a few dots on the page, and then gradually we see this pattern forming. In these top three, it still very much looks like a series of dots, but as that light is either left to shine for longer, or the light becomes more intense, it becomes more like this sort of image we see with a laser, where we can't actually anymore see those individual dots, but we just see that overall interference pattern. So, if you like, that's one example of one example of evidence that shows light behaving like a particle, as in like photons. And what we're going to go on now is look at the photoelectric effect, which even, I guess if you like, more convincingly shows us that light is behaving like a particle rather than an electromagnetic wave. Okay, so before we talk about the photoelectric effect, I've got a really quick little thought experiment I want you to do. I want to pretend you are the light, so you are the light. And you're throwing a ball at a wall. Now, if you throw that ball softly at the wall, it's not probably going to have enough energy to break through that wall, so that ball will just basically bounce back towards you off the wall. But the wall won't be able to, if you like, break through the wall. However, if you throw that ball harder with high energy at the wall, that ball will be able to smash through the wall and then basically keep moving on the other side of the wall. And the amount of energy that the ball will have afterwards will be equal to the amount of energy the ball initially had, take away how much energy it needed to break through that wall. So to say that mathematically, the final energy of the ball will equal to the initial energy of the ball minus the energy to break through the wall. Obviously though, if the ball doesn't have enough energy to break through that wall, it's not going to come through that side of the wall. So we can't, if you like, measure the amount of energy the ball has on this side of the wall. So now, and I want you to keep that in mind and think about the scenario here in this diagram. This is from a simulation on the PhET website, which runs Java. I'll show you this one in class. If you're not with me in class, try and go and use this, have a play with it. Hopefully you've got Java and it can work. So what happens in the photoelectric experiment, which was very important in showing that light was behaving like a particle, and we'll come back to that in a sec, is that light was shone onto a metal plate. So here's a light with certain wavelength or frequency. Wavelength and frequency are directly related, and intensity. Shined onto a metal plate. Here this one represents sodium. And what will happen is, if that light has enough energy, it will knock an electron out, just like you could throw the ball through the wall. And that electron will then go across this plate, setting up a flow of electricity in this circuit. So we can tell whether electricity is flowing in this circuit through measuring the current, and by measuring the voltage we can tell how much energy these electrons have, because voltage is a measure of the energy of the electrons. When we do that, we get an result, and we're going to look at this in more detail on the next slide, that looks something like this. Initially, we see the light, no electrons are being released, because the light initially at low frequency doesn't have enough energy to knock out the electrons, just like the ball not having enough energy to get through the wall. And then eventually we start to see electrons flow, and we see this sort of relationship in the between the energy of the electrons, the maximum energy of the electrons, and the energy of the light. We'll explore the nature of that relationship and why it's that shape in the next slide. But why was this result so important? Well, the reason this was so important is a guy who you may have heard of by the name of Albert Einstein used this to convince people that light was behaving like a particle rather than a wave. So if it was just like an electromagnetic wave, we would expect if we increase the intensity, it wouldn't matter what colour light. If we increase the intensity, we would increase the amount of energy striking this plate, so therefore eventually we would see electrons flow. However, that was not the case. If you have low frequency, low energy light, it doesn't matter how intense it is, you will not see a flow of electrons through this circuit. What we did see though, as we increased the frequency of the light, so came down towards the blue violet end of the spectrum, that at some point, this point here, at this frequency, which we call the threshold frequency, we'll talk about that in the next slide, we eventually saw the electrons flow. So it was like we had to have, it was like the light was behaving like little particles, and they would only make electricity flow when, if you like, they had this enough energy to break through the wall, or in this case, break out of the atom. So this was actually evidence that each of those photons was behaving like a little particle, and it could only knock an electron out with sufficient energy. It wasn't behaving like this constant stream of electromagnetic waves that we would expect. We could increase the energy by increasing the intensity, therefore eventually the intensity, if the intensity was high enough, we would see a flow of electrons. That was not observed. So let's think about what result we might see if we did the experiment that we just talked about on the previous slide. If we had on our y-axis here the kinetic Kmax, which is the maximum kinetic energy of the emitted electrons. On our x-axis, we had the frequency of the incident light, which is basically a representation of the colour of the light. Obviously, the blue-violet end has a higher frequency than the red end of the spectrum. And if we plotted those results, and we'll think about just the metal here in red first, what we would see is initially we would see no electrons flowing, so we wouldn't be able to measure the kinetic energy until we got to this frequency here, which we call the threshold frequency. So this is the minimum frequency at which the electrons are emitted. So threshold frequency, the minimum frequency at which the electrons are emitted varies with the type of material and is called the threshold frequency. So if we used a different metal, so if we had two metals here comparing metal 1 and metal 2, those two metals would probably have a different threshold frequency, with different amount of energy would be required to knock electrons out of them. So after this point we would see a linear relationship between the maximum kinetic energy and the frequency, and the slope of that would be given by Planck's constant, which is h. And we will do this experiment in the lab and you will actually work out a value for Planck's constant. Now, that slope will not change as we change different metals, because that slope, if you like, comes from the relationship of E equals hf. So the energy is equal to Planck's constant times the frequency. So the energy that the electrons will have as the frequency will depend on the frequency of the light and Planck's constant, and that will be the same for any different metals. All that will change will be this threshold frequency. So the threshold frequency, if you like, is our x-intercept. If we extrapolate these lines backwards to our y-intercept, this tells us the work function of the two metals. So 0 here, down to here, this value here is a measure of the work function, so that is the energy required to knock an electron out of metal 1. Here, this one, W2, would be the minimum amount of energy to knock an electron out of metal 2. So let's look, how would we describe that result mathematically, like with an equation? So Kmax, which is our value of y, is equal to hf. So that line there has a slope h proportional to the frequency minus the work function. So minus the y-intercept, if you like, which is it's a negative value. We're going to have a negative value here, so the work function, if you like, is a positive value, but we put the negative in front of it. So that function there describes the result of this experiment. Now, what I think it's worth doing is rewriting this slightly differently just to show how this fits with conservation of energy, which we talked about on the previous slide. So the initial energy in this case, so the initial energy is equal to the energy of the light. That's how much energy is put in. That's our initial, if you like. And the final energy is equal to the energy of the electron plus whatever the work function is. So the energy that needed to knock it out of the atom, knock through the wall. So that's equal to Kmax plus work function. So that's just what's written there rearranged. So initial equals final. Therefore, we've satisfied conservation of energy. So the type of problem solving you expected to do here is basically using this relationship and then finding normally an unknown. And it's really just like what you might have done in secondary maths, solving linear equations. It's just of the form y equals mx plus c, and you're basically solving problems using that linear equation.